Okay, so I'm here as part of the ISO TC67 WG4, we're Group 4, Project Group 1. We have a couple other representatives in the room. We have Runar Ostebo, who's the convener, and we have Stefan Isaacson over here, the Norway expert that's in our group. So we think there's a lot of good things that you can do with the 14224 standard, collection and exchange of reliability data for equipment, and we're going to talk about actually extending its use today for use with risk management. Okay, so I'm going to give a quick presentation overview to kick things off here. We're going to talk about business value first and why it makes sense to do digital transformation. And we're going to talk about a couple different words that you've probably heard, digitization versus digitalization. Then how application of the 14224 standard in your enterprise software can enable digitalization and real-time risk and reliability management. We're going to look at data quality management, take a look at an industry application example, and then ISO 14224 application and technology development and qualification. And after that, we're going to wrap it up. It's going to be kind of a full 20 minutes, so let me get going here. So business value from digitalizing equipment reliability and risk data. In a nutshell, it helps you make better decisions for your equipment, minimize operational risk, and optimize production and profitability. So the ISO 14224 standard provides a data structure for digital transformation, a tool set for data-driven decision-making, and it gives you a corporate view of equipment risk and reliability versus health, safety, and environmental considerations and profitability. And so what we're looking at here in the figure is actually a plot that shows the risk across an organization. So we actually think that you should be able to look across your enterprise globally and generate a plot like this. Where do you need to be concerned about your assets, right? And we think digital technology can give you that plot. And we're going to talk about how to get there. All right, so risk management, real-time risk management we think makes sense now. Risk assessment is nothing new to people. I'm sure everybody here that's in an operating company has already done this using traditional methods, LOPA, HAZOP, RBI, et cetera. We do a similar process with each. We generate risk scenarios. We do initial risk ranking. We look at safeguards in place and how much are they mitigating risk. And with our existing setup, is risk acceptable or not? Do we need to implement additional safeguards, right? And then once we've done the additional safeguards, we rank the residual risk again, then ask the same question, is it acceptable? But when we're doing this, what we're doing is we're taking credit for things. We're saying, okay, I'm going to do this stuff, and I'm assuming a certain level of risk reduction. But how can we reasonably and practically validate that we're actually getting that level of risk reduction? For all these scenarios that we generate, many different installations across the world, you're probably looking at maybe 10,000, 20,000 scenarios possibly per installation. It's a lot of stuff to ride herd on. And it's challenging, and that basically what I have seen in my 30 years of experience is a lot of this is actually managed in free text type format. And we'll take a look at an example. Very difficult to work with, right? So if we digitalize this, it gives us new capabilities. We can leverage new business value out of that information. Okay, so now we have big data analytics. We have the IIoT sensors, the Industrial Internet of Things sensors out there that can give us real-time process data. But we also have ERP systems where we collect a lot of information on how our facilities run, such as equipment reliability and maintenance data. Spare parts availability. I might be taking credit for a spare part. In case I have a pump outage, I have another I can put it in its place to avoid the risk of lost production. Inspections. Personnel qualifications. Who's working on this stuff? Are they qualified? I need to know that. I need to know that right away. I don't need to know that 5 years later when I do a validation. That's OSHA's requirement. It's every 5 years, right? So business requirements, the ability to analyze multiple data sets simultaneously and practical, quick to use. I want to be able to see it like real time. I don't want to wait 5 years to see if these things are really working. That doesn't really fit with what I think makes sense for managing our facilities better and having this information readily available. You need to be able to look across your facilities and know, like within the hour or day, that there is an exception and get a red light that indicates that. And that's where your big data analytics comes in. There's a lot of horsepower behind big data, and it can give you that type of a display. Okay, so let's take a look further here. Let's talk about digital transformation. And I kind of look at this as the evolution of data. I started work in '87. I didn't even have a computer, right? Everything was paper. And so really the first step is digitization. Digitization is taking the paper files and moving them over into an electronic format. So if you take an SAP or an Oracle, something like that, an enterprise resource planning tool, they are relational data applications. But there's two ways you can put information in. You can digitize it or you can digitalize it. So digitize is just taking your manual files, scanning them, putting them in free text, and sticking them in your software. No real business benefit gained. Conversely, digitalization, you're turning your data into relational data. You're integrating your information, right? So the definition, courtesy of Gartner, is the use of digital technologies to change a business model and provide new revenue and value-producing opportunities. All right, so let's look at a risk scenario. We're going to compare digitized versus digitalized, and this is for an ESD23 fail to close scenario. So if we look at this, it's a bunch of free text. The what if. Emergency shutdown valve 23 fails to close when needed, right? So it's all there. The information is there, but it's just not separated out. I need to be able to see ESD23 in a separate field so I can query a data set for that. I don't want to look at this. I don't have time to look at this stuff one scenario at a time. So I need the consequence ID broken out and registered separately. Same with the probability ID for that consequence. And the safeguards. When you look at the safeguards that are listed here, I can't go to the CMMS or the ERP system and pick that out. It's very vague. Specific inspection, testing, maintenance program for ESDs. Well, that doesn't tell me a whole lot. Okay, so I don't even know what they are. I don't know what the plan numbers are, when they're scheduled, how have they been executed, and what the results have been. Right? How can I tell? How can I get there from this? I can't do it. I'm looking at, like if I did this, if I was in a facility and actually did this, I'd be looking at 2 to 4 days of work of following up on the scenario just to find out if the enterprise is doing diligence here, right? And if you have, you have 100,000 scenarios, how are you possibly ever going to do that? The answer is that companies don't do this, not frequently enough. Okay, so how can we change this? It's not that difficult. We have the information. We just need to restructure it a little bit. This is what we call digitalized transformation. So we take the ESD23 fail to close scenario and we put it in an SAP. This is an example of an SAP system. The database systems are not that much different, right? We have a place to put the reference object, the ESD23. So I do it this way. I can query that record. The failure modes, I use ISO 14224 failure modes to describe the scenario. Valves, fail to close on demand. I can query a data set now and I can say where across my enterprise, globally, where do I have that scenario? Where am I dealing with those? See, when I break it out like that, I register it differently. It makes it much more usable, much more available, right? And other things, the codes that we have in the 14224 are useful, are actually intended to describe actual failures. But when we do a risk scenario, it's a hypothetical thing it really is a failure scenario, but that we think is possible. So the codes can work for that too. And actually, when you do it that way, all of a sudden your risk data and your reliability and maintenance data can be integrated and dovetailed very nicely. Okay, so all the things that you need to collect for a risk scenario, capture them discretely so you can query by those values. Right? So that is the difference. Okay, so how do we get there? Let's take a look at the ISO 142 data structure in the context of equipment risk and reliability and maintenance data processes. Now, I've taken the liberty of coloring the ISO 14224 processes in OTC blue today. So what they are, we have taxonomy classification. We have technical hierarchy that we can build from that. Standard equipment failure reporting processes. Preventive maintenance and inspections, results, recording, and analyses, and equipment reliability metrics. So I'm going to take a look at these, and I'm going to show you how to use that to actually set up your data and start collecting data this way. Okay, so taxonomy classification. here is the data architecture that we have in the 14224. We have use location data, how the equipment is being used. We have industry, business category, installation, plant, unit, section, system, right? That's the operating context of the equipment, right? Then there's the equipment itself. We have a main unit, we have major groups of components, and we have components. So the main unit is taxonomy level 6, subunits 7, components 8, okay? And we're going to look at these numbers in the next figure, so remember those, please. All right. All right, so here is a setup. I hope people can, I don't know if people can read this. I apologize for the small print. This is a compressor installation, a K102 compressor at a midstream operation, Pembina pipeline. Okay, so we can kind of talk about the structure, 3 different segments. We have something we call an asset register. It's a way of grouping things. So we take, like the installations, the business units, we group by that. So these are all administrative or grouping levels. Within those, we actually install equipment objects. We take this K102 compressor, we've identified the main unit, we have subunits that are designated by category 7, and then we have components. And I can draw a box around the boundary. And that's important because when I talk about equipment, I need to have consistent definitions between different people that use the system. Like, if I talk to 1,000 different people, sometimes there's more than 1,000 people putting information into a system. I need to ensure that they have a common interpretation of what a compressor is if I'm going to get good data for that compressor from all these people. So if we hard code it into the structure, the structure of the equipment, into the technical hierarchy, that ensures one consistent definition by all people that use the system. And we do this for every piece of equipment. All right? So it's not that hard. Let's look at how that works. Okay, we start with technical drawings. This is a P&ID for the K102 compressor. Now, typically, you're not going to have a boundary definition drawn on there, but I put that in there just for the benefit of the people in the audience, right? You can go back and look at it after the presentation. But normally, you just have these drawings. You have the package drawings as well. Typically, the P&IDs don't have enough on them, right? So I get a list of tags off the technical documents and drawings. Then I go to figure A2 out of Annex A in 14224, which is the boundary definition. And for each tag, I just ask a simple question. Is it in or out of the boundary? Okay, easy question. So that, if it's in, then I go to the next step. And this is equipment subdivision. So I look at the subunits, like power transmission, compressor, control and monitoring, lubrication system, etc. And I say, okay, so this tag, where does it fit in there? And I map it into that segment, right? And there you have it. You have your structure. Okay, so here's a drawing of that. Here's the figure 3 from ISO 14224. And what we're showing here, we capture the use location data using characteristics. So class and characteristics are a good way to describe how an equipment is being used. We find that works a lot better than trying to build that into the technical hierarchy itself. So this is what we call guidance on architecture of your system. All right, so the technical structure itself, basically equipment unit, subunit, component. Draw a box around it. And that box, anything that happens in that box, that's a failure of the compressor. The compressor is simply the sum of its components, right? And so we need a way to aggregate the information to the main unit. And by structuring it this way, you're actually telling your system how it's organized. By giving it a 6, 7, and 8, it knows what the components are, what the subunits are, and what the main unit is. And it can, with the right information, the right programming, you can make it do that for you. All right, we have also dedicated equipment. That's in the yellow shaded part. So if it's dedicated to the equipment, we structure it subordinate to it. It's not included in the boundary, so it's actually not in the box, right? So that is, in essence, the nuts and bolts of the structure. And one other thing I want to point out, when we collect this information, it's very important to have a structured way to put it in there. When we talk about characteristics, if it's a text type characteristic, you need to have a value set. See, there's structured data input for these characteristics. That's shown up in the the top right-hand side of the slide. And 14224 gives you those values as well in Annex A. Okay, so we build a structure like that. Now we're equipped to collect data. So we're going to talk now about failure reporting, equipment failure reporting. In ISO 14224, we have Table 6, which designates which failure data you should be collecting. Table 8 specifies maintenance data you should be collecting, right? Similar type information. I'm just showing Table 6. So I need to make sure if I'm going to digitalize my information, I need to make sure there's a blank, there's a data field in the system for putting that. I don't want to put it in long text because to me it's a very little value there. So things like failure mode, it's a normative field, right? Normative means you have to do it if you want to comply with the standard. We have a blank in here for failure mode. This is a work initiation report for the K102 compressor. So when I do the drop down on the failure modes, I want to see relevant information. I want to see failure modes for compressors, and that's it, right? And so there they are. And there's context in there for the failure modes. So if somebody has questions, now maybe it's a longer description and some context on the methods, right? So part of this as we think about, as we're doing this, we're using our systems. We need to leverage them, not to kind of make it more difficult to get the information in, but to actually assist users in making sure they get it right. These are all what I consider to be quality assurance steps. These are things we do to help assure that the final product is going to be correct. Okay? And we can validate the information. We're putting information into the system that the standard specifies we need to collect. We can use the system to check it for us to make sure it's going in a compatible way. Right? So here in this particular step, we're reporting that there is a problem. We're basically putting something into the system for the maintenance department to take a look at. We don't have all the information, but we validate a partial set here. Okay? This goes to the maintenance department. The equipment gets fixed. And the next thing that we see at the end of that cycle is the equipment closeout, the work order closeout for the failure report. And here we're doing component level notations. So what we do at this step is we specify the primary failure component first. So I pick again from table A9. That's the table we looked at previously that has the subdivision of the equipment. So again, I have structured input for specifying the primary failure component, and I can also add in corollary damage. So primary 1, corollary 2, 3, 4. Right? Then I specify a failure mechanism, and note table B2 and ISO 14224 provides information, structured input for that. I also have long text, additional information on those failure mechanisms. And we also have a step, this is like the closeout part, we know things like, for example, malfunction end date, right? You don't know that till the end. We validate the balance of the information at this point in time. But we're not quite done yet. Okay, we also need to be able to collect information that describes how much it affected our operations in the way of consequences, health, safety, environmental, and profitability for each event. And please don't groan, but it's important. If you want to measure and improve these things, you need to collect the data. You need to measure it. So it's quite simple. If we use our table C2 out of the 14224 standard, we can designate. In fact, you can make this part of a shop paper. You can circle the items that are relevant for that event. And you put it in your system, and all of a sudden you can look across your global operations. You can say, okay, so for everything, all the failures I've had, you can pick specific things. You can say, I want to see all my pumps in like crude oil service. What are the failure consequences over the past year for those pumps? And I can get it across all global operations. I can run this plot. This is an SAP plot. Standard SAP will deliver that for you if your data are structured properly. Okay, so here's a couple other examples of metrics. So we talked about real-time risk and reliability. Okay, so at the top left-hand side, what that shows is a global plot, and each dot represents an installation. And we have a color code, red, yellow, green. So if it's red, you got to look at that. There's something wrong, not quite right. Okay? So we can go to the red dot, we can open it up, we can get an installation view, and then we can go from there and we can see, okay, so what is my risk status? There's a number of ways you can drill down. I'm just showing one example here. I can get a set of equipment that is at high risk. I can look at things like its history, its reliability, like what kind of failure modes have I seen for that equipment, right? What are the primary failure components? What are the failure mechanisms of those primary failure components? So I have tools basically to look at the highest priority things in my organization now and focus on those. All right. One important thing is you have to be able to trust that information. So we have to make an investment in data quality, right? So quality management needs to be an important part of your program. Quality management can be divided into two separate parts. Quality assurance, as we spoke about earlier. These are proactive measures that increase likelihood completed records are correct. Things like standard technical hierarchy, common definitions, everybody using the same definition for a compressor, for a pump, right? It helps make sure the end product is right. So data collection, what we looked at previously, having checks. And when people put data in, making sure it's compliant with what you need to be doing. But that's not it. So you get your end product, you need to be able to have a quality control step in there. Look at the completed records. You don't have to look at every single one, but do partial sampling. Not that much different than doing product quality control, right? We focus on the areas that need attention, where we've identified issues. And in this case, what we do is we circle back with field personnel to re-educate and to get alignment with them, all right? So ISO 9001 also talks about quality management in the context of risk. Just to talk about a few parts of it, they say a risk-based approach should be adopted. Objectives are to prevent equipment failures, mitigate severe consequences, and achieve continual improvement. It is important to have quality, reliability, and maintenance data for evaluation of the effect of actions taken, and by that allow for decision-making that is risk-informed. Okay, so collection of reliability and maintenance data is costly, and reliability and maintenance data collection effort should be balanced against intended use and benefits. Yes, agreed. But one thing I'd like to point out is that if you collect data, if you get it right at inception, instead of going, I've seen a lot of activity where people go back at a later time. A data collector goes back and tries to sort out inadequate data. It's much more costly to do it that way than to get it right the first time. Okay, so I promised some discussion on application of the 14224 to the ESP RIFS JIP. One of our co-authors, Francisco Al-Hanadi, is heading up that JIP, and they've been using ISO 14224 methods for, I think, about 20 years now. So what they're doing is consistent. It's not exactly what we have in our standard, but it's consistent from a methodology perspective with system boundary, failed items, failure mechanisms, and failure causes. It has been adopted by ISO 15551-1. So some of the benefits that they've seen, operators are able to make more informed design decisions, such as motor model intake pressure, to identify main failure mechanisms of concern and to guide collaboration with manufacturers. So it allows for investigations on the effects of equipment trim and operating practices on ESP system reliability. So they're looking at some new things now in the context of real-time data. So models are being developed to predict probability of failure as a function of equipment characteristics and real-time operating conditions. This allows operators to determine when it makes sense to implement changes in operating conditions, to extend run life, and or to schedule preventive pulls to minimize production losses. Okay, so we also promised to talk about technology development and qualification.
Could you make
so ISO
a
14222
conclusion? I think.
Do we need to conclude?
Yeah.
Okay. Okay, so that's some homework for you guys. So concluding remarks, digitalization and big data analytics give oil and gas companies new potential to transform oil and gas operations to be more sustainable, safe, and profitable. The 14224 standard provides a data structure and methods for digitalization of equipment reliability and maintenance and risk data. And from a standards perspective, we think standardization is important, and ISO standards are key to achieve business objectives. So with that, I'd like to thank the ISO TC67 management and my co-authors from Equinor, Norris, and Seafer Technologies. And I don't know if we have time for questions.
Thank you, Tony. It was a quite intensive paper we need to look at, and talking about some digital transformation and kind of data quality. Maybe you need one question from the floor? Okay.
Sure.
But make it short.
Maybe a short question. David Cameron, University of Oslo. If I was an operator who had a legacy SAP PM or Maximo system, Can you comment on what sort of effort you'd have to do to get this system implemented?
We'd have to take a look at it to see the state of your data. I mean, an SAP system can be used different ways. I mean, some companies have done a good job of digitalization and following data standards. Some haven't. But typically, it's a matter of setting up your technical hierarchy, and then you can, since the methods are standard, you can actually put the methods into your system fairly quickly. The hard work is really putting your structure together.
Right there. Thank you.
Thank you, Tony.
Thanks. Sorry to run over there.
All right.